two of them to have a deeper study. The rest will be in the textbook, which I won't test you. I won't test you in depth, but it doesn't mean that I won't test you what is current feedback, right? To figure it out what type it is. Okay, so let's look at this voltage feedback. Why it is voltage feedback again? Because the input to the feedback amplifier is voltage. The output from the feedback amplifier is also voltage. That's why it's called voltage. And can you remind me again, if from the whole circuit topology, in terms of shunt and series, what do we call this? Series shunt. You don't need the cheat sheet, right? Cheat sheet is only for you to double check. Because you see clearly, input is connected in series, right? Output is connected in parallel configuration. Okay, so this is series shunt. Okay, so can you tell me what is the open loop gain of this circuit?
A naught over 1 plus Ka naught.
I say open loop, yeah. A naught, yeah. You know, you guys are very smart, but sometimes too fast. And then I cannot give you partial credit when you give me this answer. Okay, closed loop gain is A naught over 1 plus K A naught, which you learned before. And then what is the feedback factor? By definition. Oh, just not definition, just give me the symbol. You don't need to calculate. It's what? K. I'm not asking for VF divided by VL. Yeah, good. Okay, so this one looks easy. Then we would apply it directly to a real circuit. We learned these circuits before already, right? So we will repeat some of what we have discussed before, but this time I want to go a little bit in a different direction. I want to map this one to the circuit we have, right? The first of all, I say this is a feedback, voltage feedback. Do you agree? Yes. Even you cannot decompose it, right? And you assume that I'm not tricking you. This is indeed a feedback circuit. Then you of course know that this is correct because input to the whole circuit is voltage. Output from the whole circuit is voltage. So the inputs to the feedback network must be voltage, right? The output of the whole circuit is the input. The output of the whole circuit is the input to the feedback. And then the input of the whole circuit is the output of the feedback amplifier, right? So it is voltage, right? That's first thing. Now, so let's try to decompose this from another angle, right? Or not angle, just from another drawing, which we learned last time already when we are trying to do the loop gain, right? But now I just look at, I'm not playing with loop gain. I just look at it as a whole circuit. So I want to do this step by step. First, how do I decompose this circuit? Right. I have an input here, V in, plus minus, and then I want to map it to A naught. And then I have a K, yes. Someone says it's related to the differential amplifier. So, okay, I just draw the circuit, right? Now, we'll try to map it. Then I try to morph it slowly. First, I will say, how do you do comparison? This is just like a, how do you call this type of drawing? I mean, just it's not really a, no, I mean, the way we draw it is not really a circuit, right? It's just a descriptive block diagram or something. Yeah, thank you. Yeah, so maybe I will say hey, actually, to do this, I can do what we are doing here, something like this, right? So how about this? I assume that A naught, this one comes in, okay, make it a 2-pot maybe, and then this V in, and then this is the feedback, VF, then isn't that this part? I call it VE equals to V in minus VF. Do you see this? Because VF plus VE equal to V in, right? If you cannot see it, V in is a voltage source from previous and reference to ground, right? So just by KVL, this part is V in, and this part is VF plus VE. So VE equal to V in minus VF, right? I have experience, so I can write it right away. Otherwise, you look at it for a few moments, you'll find that that's what you get. Is this okay? And that makes sense. I'm doing the subtraction. Okay. So, okay. Then I have V out here. And of course, for sensing, I just need to take this to here. Right? So gradually, I move to here. And then I will say, based on this, right? This is V in. This is V out. And then I have something comes in to do the subtraction. And this one you need to apply your knowledge right away. That which part of this can really do this correctly, right? So you can keep trying, but based on my experience, right, I immediately see that, hey, this part, A0, I take it out. And then this is VF. This is V in. And this is V out. It's very similar to this one. V out equal to A0 times V in minus VF. Correct? This is just an operational amplifier you learned in lecture 1. A0 times V in minus VF, right? One is plus. Maybe I should make it clear, right? Maybe this is plus. This is the plus terminal. This is the minus terminal. V out equals to V in minus VF times A0, right? And now you see that, hey, this is just equals to this circuit. V in. If I say this part corresponds to A0. Make sense? Because this part will have a V out, and then it has 2 inputs. And I remember this is what? Single-ended differential amplifier, and the outputs equals to GM N times RON parallel ROP. You really should memorize this equation, right? Even if it's not in the final, the simplest one. Times what? V in minus VF. Thank you. Remember this? It's very similar to a common source amplifier, but it's differential and it's single-ended, right? So isn't that this achieved the goal of comparison and also forward amplification? Any question? Right, so in your exam, you need to have the ability to decompose the circuit into this part. Because once you can decompose to A and K, then you can use all the equation we derived earlier, how the input impedance will be modified, output impedance will be modified. Okay? Any questions? Think about this. So I'm pretty good now. This is easy, right? I kind of finished the comparator and also finished the feed-forward. Then how about the feedback? Which part is the feedback? Yeah, naturally, then you will think the rest needs to be the feedback, right? Because the feedback plus the feed-forward and comparison, sensing. And sensing and comparison usually do not have their own component. It's just a wire, right? And in this case, it is the same. So regarding the feedback, then I will claim that, yeah, like what you say, voltage divider. This is output. Then I have R1, R2. Then I take this part as VF. Then everything just like a puzzle, they match. V out, VF, and this VF comes to here. Okay? So then what is the feedback factor? Right, based on this. This is what we are doing. This is VF, and this is V out. So what is K based on this? K is VF divided by V out, right? So K equals to R2 divided by R1 plus R2. Okay, so after this decomposition, I know a lot about this amplifier. First of all, what is the gain of this whole thing, this whole circuit? If you see this is in E122, you will not attempt to solve it. 4 transistor, 2 resistor, and you completely don't know what it is. Looks like differential amplifier, but it is not. And only have 1 input, not 2 inputs, right? But now you can tell me right away, what is the gain of this whole circuit? Say again. Say again.
VO over 1 plus K.
VO over 1 plus K. Why you say VO?
Oh.
Okay. Oh, you say VO because I have a
You
typo.
have labeled it.
Yes. Why you did not say that I'm wrong? Should be what?
AO.
AO, right? So I keep thinking why you say VO. But it's not my mistake, it's your mistake to follow the mistake.
Whoa. I adopt any convention proposed by the person who is leading the class.
Good. Yeah, thank you. So I have a lot
Want to
of.
label?
Okay, so all of you are right? It should just that my
Well,
mistake
just submit our grades down. You know what
for today, but there's no score for today. Very good, right? AO divided by 1 plus KAO, right? So I just plug in, this is GMN, RON parallel ROP. No, I'm right. Come on. I'm right. This is indeed VO.
So technically you would need AO, which would be GM or parallel.
No, so first of all, this is VO because it is the gain times the input. So I'm right in terms of this. But now you want to put is AO, right? The gain. So which is only this part. Okay? Yeah. So then the whole thing divided by 1 plus this one. Again, the whole thing. And then multiply by this K, R2 divided by R1 plus. Can I write? I'm sorry. Let me redo it. Right? It should be 1 plus GMN R0N parallel ROP times R2 divided by 1 plus R1 plus R2. Is this okay? Yeah. So now the reason we learn all this theory is that now you can handle this circuit so easily. And why you need that? Because it's meaningless to solve a circuit people already know. It is that in the future you can come up with your own idea and you use this method to help you to design the circuit. Right? You can have your own version of feedback. Right? And in your mind you have a purpose. First, I just want to have a high gain. Then you run into a lot of problems like stability, variation, bad input, bad output impedance. Then you think about feedback. And then with the knowledge of feedback, you will be able to find the gain easily. They might not be correct, maybe only 90% correct, 80% correct, doesn't matter. You use SPICE to do verification. Okay? So, is this clear? Okay. Now, then how about the input impedance? This one we derived before already. I'm not going to re-derive it, but just want to remind you. For when we have a feedback, for a voltage feedback, what happened to the input impedance? Is it getting to be larger or smaller when we have a feedback? And the first thing is, remember, you want to go to a more desirable, better. You want to make it better, right? So what is the input for a voltage feedback? Right, but let's answer this question. What is the input to a voltage feedback? The whole circuit. Again, right? Voltage feedback means the input to the feedback is voltage. Output from the feedback op amp is voltage, right? But how about for the whole circuit? What's the input? Voltage, right? Because the output of the feedback is the input of the whole circuit, right? So it's voltage. So when the input is voltage, are you sensing or, I mean, as the amplifier, are you sensing or delivering voltage? No, you are the amplifier. I'm talking about you are the amplifier and the input is voltage. What are you doing? The input is voltage. Input is what you're trying to sense, right? So it is voltage. So if you're sensing voltage, what impedance should it be if it's ideal? Infinite. So you want to make it large, right? So going through all this, maybe your cheat sheet already tell you the answer. That is fine, but you need to find a way to memorize it or to check it, right? So it turned out the output impedance is equals to the original one times 1 plus Ka0, just like in the last lecture, right? We discussed this. Okay. That's it. Again, I did not derive anything. I already know this is the answer. And I don't need to memorize, right? I only use the cheat sheet to check. I did not look at the cheat sheet. Is that okay? So let's go to another example. Right? Getting closer and more similar to our exam. So, can you make sense out of this actually? Someone want to decompose this circuit and say something about this circuit? Voltage in, voltage out, very good. And since you're answering the question, maybe I keep answering, right? So, okay, maybe no. Okay, voltage in, so voltage amplifier. Okay, can you go deeper because now it's not a block diagram, right? Can you tell me what it is and common gates? Very good. But this is not connected to constant, right? Which is okay because we're doing feedback, right? Right. The point is whether we can map it to a feedback circuit, right? Map to this one, right? This one. And you say it is voltage, so I'm going to map to this one because it's voltage. Okay, good. So, okay, right, voltage. How about the feedback? Where is the feedback then? VF. I mean, the feedback amplifier is this potential divider, right? Yeah. So basically, you already found it, right? Then we can do this. Without the feedback, it means what? R1, R2 has to go, right? To go, right? So this is constantly biased. And this is what type of amplifier? You just told me it is common gate. So without feedback, what is R in for a common gate? 1 over GM. I ignore channel length modulation. Isn't that 1 over GM plus RD? No, okay, great. It's no, right? Yeah, because the reason we get 1 over GM is that we solve the small signal model and we find that RD has no effect when the channel length modulation is not much or you have very large RO, right? What is the feedback factor? K equal to R2 divided by R1 plus R2, okay? So based on what we have learned, what will be the input impedance of this new circuit? One over GM times 1 plus. Okay, let's do it slowly. R2 divided by R1 plus R2. That is because this is R in without feedback, right? And this is K, but we have forgot to find out what is A0, right? What is A0 for the circuit? Not necessary. Yeah. Okay. Someone say something. What is that? GM RD. Why? Because it's the gain of the common gates, right? So I should have said this earlier with A0 equal to GM RD. It's not negative GM RD, right? If common source negative GM. Is the units correct? Let's take a look. GM RD is what? What unit is GM RD? No unit. R2 divided by R1 plus R2, no unit. Unitless plus 1 unitless. 1 over GM is resistance. Correct, R in. Everything makes sense, right? If you do not get this, then you know that you did something wrong, right? We made an important assumption is that R1, R2 is much, much larger than RD. Because for the methodology we are using, we assume that this one does not cause any problem to the previous stage, right? So this one, you need to be careful. Not for this class, we don't test this. In the Razavi's book, right, he did discuss what if that is not the case. You need to modify the equation. There's something you can do. If you're interested, you can take a look. But most important thing, again, everything you learn from this school, you need to prepare that they are just ideal situation. If it doesn't work, don't argue with people. It might be just that we were learning the ideal situation, right? But most of the time, it's good enough. Okay? Great. If I get everything right. Okay. How about the output impedance? Let me see how many slides I still have. Okay. How about the output impedance? What happened to the output impedance of a voltage feedback? You want it to be 0 because ideal
voltage source.
Ideal voltage source. But if you write that in your exam, I really don't know what you mean, right? So be careful, double check. So the R out dash equals to R out what? Over 1 plus KA0, right? Again, this can be in your cheat sheet. But okay, now let's look at this circuit, which we just studied, right? So it should be easy. Without feedback, what type of amplifier again? Do you remember the name? Without the feedback. No. I'm not talking about. First of all, okay, this one maybe you feel confusing, but this is the same circuit. This is V out. Okay, this is just the drawing that we try to find the output impedance. That's why we apply a test source here, right? But now we don't want to do this small signal. Just this circuit without feedback. What type of amplifier is that? Differential amplifier, single-ended differential amplifier, right? For M2, but I'm saying without feedback, right? When there's no feedback, no, then it is still differential, right? Then it is, we cannot say it's the circuit is differential, but you're not applying, in this whole process, you are not applying a differential signal. However, the equation is still correct, right? So this is single-ended differential amplifier. The reason we want to identify this is we want to know the equation, right? So what is the gain of this open loop gain? What's the open loop gain? We already mentioned GM, RO. Okay, can you tell me GM what? GMN or GMP? Huh? N. Because it's just like a common source. GMN times GMP parallel ROP, right? Oh, of course, it's not on this branch, it's just overall. We did not derive it, but we say that this is correct from the textbook. Without feedback, what is the output impedance of this differential, single-ended differential amplifier? What do you do? No, don't. Right, what do you see? What impedance do you see? I need to ground the input, and then I walk in, apply voltage. What input impedance do you see? It is actually a little bit complicated. You need to derive it a little bit, right? But it is good enough just to make an assumption. But we already discussed this earlier. You kind of looking up is what? Is the drain off? M4 is PMOS or NMOS? PMOS. And then looking down is the drain of NMOS, right? Now, of course, some of you may complain that, is this constant? Is this constant? Right? We don't know actually. We need to solve it. But however, after you solve it, it's basically similar to as if it is constant. So this one, you just take it for granted, and you need to agree with this without deriving. So this is RON parallel ROP, which is not surprising, but you do not take it for granted. Yeah, you take it for granted. I just gave you, right? But you need to ask all these questions because this is not grounded, right? Now, if this is grounded, then if this is grounded, it's possible that this one doesn't change. However, you apply a voltage here, right? Then there will be some change if you have channel length modulation, right? So it is not really at zero. This is not really at zero, right? But if you solve the circuit, it turns out that this is a good approximation, right? What is the feedback factor here again? R2 over R1 plus R2, right? So what is the new R out with feedback? It was RON parallel ROP. RON parallel ROP, and then
O
divided by 1 plus K, and then times GM RON parallel ROP. Make sense? Because this is A0, this is K, and this is R. I'm not going to label this R out before any feedback, right? Okay, we can do that. No, it doesn't need to be negative feedback, because if it's not, then this will be negative. So is it large RON parallel RP usually? Yeah, RON is supposed to be large. But what do you have now? RON parallel RP divided by a very large term, right? If this is so large, actually I'm going to cancel this too. What is the approximate value? Yeah, it becomes, we'll just write it in this way, R2 divided by R1 plus
It's really just one over G.
R2 GM, right? Make sense? But R1 and R2 cannot be too different. Maybe 200 kilo ohm, 500 kilo ohm, only a few times, right? So this one supposed to be very large, now is only 1 over GM times, and even divided by a large number or a small number, whatever. Yeah. Yeah, so this is still in the order of 1 over GM, right? So with the feedback, originally I have a high gain but lousy output impedance. Now I have a lower gain but very small output impedance. So I'm a good voltage amplifier now. I'm a good voltage source. Okay, and again, in this case, we make R1, R2 needs to be much larger than RON parallel ROP, so to avoid the loading effect. Okay, any questions? If not, let's move to another topic that we want to discuss is voltage current feedback. Is this voltage current? Why is it called voltage current feedback? No, carefully, right? When we say voltage current, we talk about what again? The first one is what? The first one is the input to where? To the feedback amplifier. Okay? This is the output from the feedback amplifier, right? So that's why this is called voltage current feedback. In terms of the connection, series and shunt, how would you call it? Shunt. Why? Parallel, because you can see from here, right? Parallel. But we can confirm ourselves. Let's say I'm drunk, I'm not sure, right? So now, the input is current. I need to take away the current. So it needs to be parallel. You can only take away current by parallel, right? The output is voltage. I want to sense the voltage. So you only measure voltage by using parallel. So correct, I'm right, shunt, right? So what is the open loop gain? R0, thank you. Right? How about the closed loop gain? RO over K, thank you. Now, some of you was a little bit hesitated to answer, right? But again, it really doesn't matter how we call it. And when we derive this equation, A0 divided by 1 plus K0, we did not say whether the input is current or voltage. We went through all the derivation without making any assumption. So it's applicable to any of this configuration. Except that you need to be careful. Just symbol-wise, I call it RO. You can call it A0, it doesn't matter, nothing wrong. But you know that the unit is ohm, right? The gain is no longer unitness, right? And then the feedback factor is clear, so nothing. So this one is going to take a long time. So maybe I will stop here today. Okay, and then I'll continue on Wednesday. Any questions? Yeah. Shunt, no, shunt usually means parallel. You shunt something, right? You make it in parallel. So when you say make it to ground, you also need to do parallel connection to make you shunt something to ground through a capacitor or whatever, and that is a parallel connection. Yeah.
That's not
I did not. Thank you. Yeah.
Say that the output